Hello, it's my pleasure to talk about cubic splines. So, we're going to start by reminiscing about polynomial interpolation, where we interpolated on a cubic, and we're going to transition that into cubic splines, and then we're going to do a cubic spline by example. So, remember the polynomial interpolation, we had some quote unquote x data, and temperature data, and then we also had some density data. So we treated the temperature data as x and the density data as y. And we didn't really look at the viscosity values, but the temperature data in Celsius and the density data in kilograms per cubic meter. And on the polynomial interpolation, we thought about a cubic there. And what we did is of the 11 total points, we focused on 4 in the middle because we were looking at, hey, we want to know if the temperature was 75, we wanted to know what the data would predict. So what the idea of the interpolation was, we would put a cubic through those 4 points and then use that cubic to predict what density goes with the temperature of 75. So we have 11 data points, and we're focusing on 4 because we're interested in that 75. That was polynomial interpolation. For cubic spline segments, on the other hand, we actually use all of the data. So we take the 11 data points that we had and we fit cubics between each pair of points. So that means that we're going to have cubic spline, that's called a spline. We're going to have cubic splines that go between each pair of points. The first cubic spline would go between x1 and x2. The second cubic spline would go between x2 and x3. The fourth cubic spline would go between x4 and x5. And that particular cubic spline is the one that we would use to figure out what the predicted value for density is, corresponding with 75. So that's what it is. We use all of the data and fit cubics actually between each pair of points. So we're looking at, for this example, we have 11 data points. So we're looking at figuring out 10 cubic spline segments. So this is the first cubic spline segment, goes between points 1 and 2. And so we denote it as S sub 1. And we're writing it as a cubic. So we've got these coefficients, A1, B1, C1, D1. We don't know yet. And we're referencing x to go between x1 and x2. So it's reference to x1. So we take how far we're into that cubic spline for a particular x and relative to x1. And then you see that the coefficients, B1 goes with the linear, C1 goes with the quadratic, D1 goes with the cubic. So that's kind of how it lays out. So the unknowns are the A, B, C, and D. And if you've got 10 spline segments, that means you've got 40 unknowns. So there's quite a bit to figure out. So the above, this first spline segment, of course, is only active between the x1 and x2, the first and second x values. And the first requirement for the spline, it must pass through the data points. Okay, so that means if x happened to be x1, if you substituted x1 here, so you'd have x1 minus x1, x1 minus x1, x1 minus x1, that means that those last 3 terms would all vanish, and the spline should report a1. Well, it's got to equal the particular y or the function. So sometimes f1 or f is used as function of x, or you just call it as y, but that would be the density in our example. So the first requirement is that the splines provide the actual data at the point. So the first spline, we're going to get A1 equals F1 or Y1. And that helps a lot because now instead of 40 unknowns, we've only got 30 left. So we've got A1 taken care of. We've got A2, A3, all the A's are taken care of. They're going to equal, the particular data point that corresponds with that particular X of that segment. Okay, so let's bring in, next thing, let's bring in the notion of H again. So H is going to be a full step in between particular data points. So H1 is going to be between the next X and the previous X, or the current X. So H1, H1, X1, and we're looking at what happens with X1 stepping towards X2. So generically, it's HI is XI plus 1 minus XI. Okay, so what we're going to do here is we're setting up what's going to happen at the end of the first spline segment. Okay, so at the end of the first spline segment, X equals X2. So we know X2, we know X1. So we have this X1 minus, we have this X2 minus X1 thing going on for our cubic spline. Well, that's got to equal the next F2 or the next Y. So we've got that one, and we can actually put in our H values. We can substitute the H, so it looks a lot better there, and we call that equation 1813 following the book. And I just kind of colloquially call it the zero derivative match. So that's one of our equations we'll use. Okay, so now we're going to think about derivatives. So derivatives, so we're going to take our S1, our spline, first spline segment, and differentiate it with respect to X. And we're going to, of course, it's going to be very, very easy to do that. So you've got D1 X minus X1 cubed. So you're going to bring down to 3, keep the D1, and then the X minus X1 becomes a squared. Similarly for the quadratic, or the quadratic term and the linear term. Linear term, we just end up with B1. And then you repeat it again because I want the second derivative as well. So first derivative we're calling S1 prime, second derivative S1 double prime. And you're going to end up with just the 2C on this one. And then the 2 comes down with the 3, so we end up with a 6D, X minus X1. So we're making some progress here. So that second spline segment is active between points 2 and 3. So that's going to, of course, give us the A2 that we had. But let's go ahead and differentiate those as well. So those are going to be differentiated, okay? Similarly to how we did the first spline segment. And then what we want to do is we want to match the derivatives at each of the interior points. So focusing on that transition between the end of the first spline segment and the beginning of the second spline segment, we're going to have the first the end of the first, so X2 on the first spline segment derivative. We're going to have this equation, and we're going to equate that to the derivative of the second spline segment evaluated at its beginning point, which is going to be B2, right? Because X minus X2, those drop out. So that's an important equation. And then similarly for the end of the first spline segment, second derivative, right here, we want to equate that to the second derivative of the second spline segment where it begins, which is going to be 2C because X is X2. So that's 1815. That's our S prime match equation. And then we have our S double prime match equation. This one's important right away. We're going to use that. We're going to take that S double prime matching equation, and we're actually going to solve for D1. D1 is going to be equation 1818. I call it the DI equation. So we've got D1 shown here, but generically it would be a DI, and it's in terms of C. So we want to get our D and B in terms of C. That's sort of the the goal here, little thing that I wanted to mention. So we've got 1818. That's an important equation. Bring it back at 1813, and we're going to substitute into 1813 this handy D1 equation that we had earlier, and then we can sort of clean it up. Remember 1813 zero derivative match. So now we have 1819. I'm going to call that the zero derivative match without the D, no D. So we've got, basically F. We've got B1, and we've got the C's still in 1819. Okay, so if I take the 1818 and I substitute it in to the first derivative match equation, 1815, I substitute that in and do some simplifications, I get 1820, which I call the next BI equation. So, we have B1, we have C1, C2, so that gives me the next B equation. So I call it the next BI equation, 1820. If I take 1819, that's the zero derivative match without the D, I can actually solve for B1 equation. I call that the BI equation. Okay, so that's an important one because I've got, like, similarly to what I have with 1818, that gives me the DI equation. I've got DI in terms of C. Here for 1821, I've got the BI, or I call it the BI equation. I've got B in terms of the C's, and of course things that we know. Okay, so I take 1821, the BI equation, and I increment it by 1. I take everything, increment whatever number I had, I just increment that, right? So C1 goes C2, C2, C3. So I've got the next, incremented version of the BI equation. And what I want to do is I want to take these two and substitute into what I call the next BI equation. So I take this B2, substitute right there. I take this B1 and substitute it into there. So now I've got this big wad of stuff. But if you notice, the only thing I have in here that are unknowns are my C's. So that's kind of what I need. I need that the C equation. And it turns out I can take this one and simplify it a little bit more, put it into a very nice form where I have stuff I know over here, and then I have my H's, of course, over here, and I don't know the C's. So I've got a very nice equation in terms of C's. All right, so I call that 1824, and I called it the CI equation. So I kind of have AI is trivially obtained, and then I have the DI equation. Got the CI equation, I got the BI equation, I've got the DI equation. So I have what I need, really. I've just got to set them up to solve. And I said, CI, BI, DI, but, it's kind of notated everything with 1, 2, 3 subscripts here, signifying the very first spline segment that we were studying. But I could take all of those and switch. If it were a 1, I could put an I there, and then whatever was a 2 would be an I plus 1, etc. And I can generically set up my equations in terms of I. And this will help when, like, in a for loop kind of thing. So I'm set up now. Okay. So what I can do is actually set up a linear system, and so what happens is you have a linear system of equations where our only unknowns are our C variables, and we actually add a C because we only have 10 spline segments, but we go ahead and add a C, and we set C1 and C11 to 0. Now, remember, this is set up for a 10 spline example, so you could adjust to the number of splines that you need. But for the purposes here, we have 10 spline segments, so we're going to have 11 C's because we've added one, and they call it a natural spline, is where you you force the first C and the last C to be 0. The idea being that, well, you can't match slopes of the derivatives. You can't match derivatives beyond the ends because there's nothing to match it to. So how they force it to be 0 is you have your linear matrix over on the left, and its first row is all zeros except for the very first one that would be in the beginning of the diagonal. And then on the right hand side, you've got that equal to 0. So that's that first equation actually is C1 equals 0 because of that. Similarly, the last row has all zeros except for the very bottom right diagonal element 1 that goes with C11, and that's going to be equal to 0. So that forces C11 to be 0. So that takes care of the C1 and C11. Really just remains to get the C2 through the C10 now. So how do we do that? Well, we basically we implement this equation right here, the 1824. We implement the 1824 equation for each row, for each I. Let's see how that works. So for example, the very second row, the second row is going to be H1 times C1 plus 2 quantity H1 plus H2 times C2, and then it's going to be H2 times C3, and that's going to equal the right hand side would equal 3, and then I have a bracket, so the bracket is the Fi plus 1 minus Fi over Hi, and we show that as a bracket of F bracket Hi plus 1 Xi. So that's the 3, 2 in this case, and then we have the bracket of 2 of F2, 1. So let's go back and figure out what that means. So that's coming from here. Remember, if we go back and look at the CI equation before we actually did the transition to the I, this equation right here is precisely the equation I just talked about for the second row of that linear system. Okay, so that takes care of that. And then you just increment, and what happens is, the H and the 2H, the H, the 2 with the sum of the H's, and then the other H, that just slides over one column as you get all the way to the end, and then it finishes out. And then of course, the F, the 3 times the F bracket difference just percolates down, and then you have your linear system. It's tridiagonal, so actually somewhat sparse. Okay, but you can use this to solve for the intermediate C's. Let's look at some code. All right, so I've got a cubic spline function here that I want to kind of walk you through so you understand perfectly how this works. So cubic spline function, it would accept the raw data that you had, so the tabular data. In our example, X would be the sequence of temperatures, and Y would be the sequence of densities that's coming in. We'd have 11 each, and it's going to return this array or matrix. It's going to be the splines matrix would have 4 columns. The first column is A, second column B, third column C, fourth column D. And then the number of rows would be the number of spline segments that you're going to have. So in this case, I should be getting a 10 by 4 returned matrix. So that's what we're looking at. N is going to be the length of D. So in this function, N is going to be the number of points. Okay, so we're going to have 11, for example. And then here, it's we're setting up. I called it AA linear. So that's AA linear is going to be the big 11 by 11 matrix in our example. And then the BB linear, that's going to be the right-hand side. And then what we're solving for is actually going to be our C column of unknowns. Okay, so the BB linear, we're going to set up the first row of that. It's just 1, 0. So I'm kind of just walking through. So I've got that right there. That right there is what is the very first one. And then my AA linear, so I'm going to initialize it as all zeros. So it's going to be a 1 by 11 in our example. And then I kind of clean it up to set up that first row, the first diagonal element to be 1. So these two statements take care of that whole row right there in that first in the big matrix. Okay, then just kind of matriculate through and just go row by row, really, row by row, filling out both the AA linear and the BB linear thing. So BB linear, I take the previous BB linear that I had. Semicolon means that this is working on the next row, and that's taking care of my 3 times, the BRAC 2. So here's my BRAC 2. BRAC 2, same one that I used in polynomial interpolation. So that's taking care of my BRAC 2s. So my BRAC 2s are coming in and taking care of, the right-hand side over here, the 3 times the difference, the FBRAC difference. And then my AA linear, keep what I had before and just concatenate the next row. I just initialize the next row to all zeros, and then I go in and put the and walk out. So II is going to be my my diagonal, and that's going to be 2 times the difference in, so these are H's, the difference in X data, those are H's, and see what that looks like here. Going back, so for example, the first row, that diagonal would be H1 plus H2 times 2. So that's what's going on here. And then I kind of fix up the location to the left of the pivot would be this, and the location to the right of the pivot would be that. So left of pivot, right of pivot, and that takes care of the AA for that row. And then I just go all the way till the next to the last row. So in our case, it'd be the 10th row. And then I finish up the 11th row, same kind of complementing what I did up here. Fill out, initialize it to all zeros for the A. Put the bottom diagonal piece as 1, and then finish up with the BB linear of 0. So that takes care of that bottom row equals 0. So it would give me my C11 in this case. And then I solve, just use the left-hand divide and solve for my C's. So C is going to be a column of C, so 1 through 11 in our case. And what I do is I go and I use my AI, so that's going to be the data. So AI, very, very trivial there. So, and then the B's, and I'm going to use the B equation, right? If I go back to here, I'm going to be using that 1821, the BI equation. Go back here, right? So that's the BI equation. Check me out. Okay, and then I have the DI equation right here. Go back. Right there, 1818. I called it the DI equation. All right, so I've got my C's taken care of. I got my A's taken care of. I got my B's taken care of. I got my D's. So all I need to do now, I had initialized splines to be empty. So first time through, I'd have empty concatenating with the very first spline segment, A, B, C, D. And then second loop through the for loop, I would I would take the previous spline matrix and then concatenate the current spline as the very next row. And then at the end of the day, I have my the number of splines. So in this case, 10 by 4 matrix is what's being returned out of the function. Okay, so that's how you get your spline data. It corresponds with your raw input data. And then how do I use it? So here's that temperature array vector, and then my density array or vector, right? So I've got that, and then I go ahead and use that XD YD data. I put that into that cubic spline function. So now I've got my splines. So splines again, 10 by 4. And then there's that point of interest that we had at the beginning. I've got, X 75. I want to know. So I've got a cubic spline get Y. So I give it the splines. I have to give it the X's because I have to figure out, hey, where is this X? I got to figure out which spline am I in. So I need to send it the splines. I need to send it the X raw data. And then here's my current point of interest, the XI. And then I've got the spline I. So this spline I, Y spline I, will correspond. That's the one that we want to find out. What's the data telling me that goes, what was the density here that would go with this 75 temperature. So this cubic spline get Y. Let's take a peek at that. So cubic spline get Y, you're bringing in your splines, you're bringing in your raw data, and then here's the point of interest. So you have to figure out how long it is here because you wouldn't know otherwise. And then what you're doing is you're comparing the point of interest, where is it? And as you walk through the X data, you're comparing it to see if that X is between the beginning of that particular spline segment and the end or the beginning of the next spline segment. If it is, you break, and then that current I is what you want to use down here in the splines. So that's how that's how it works. And once you know that I, then that sets, you use the XD as we had at the beginning to reference for that particular spline. And then the X is coming in, the point of interest is coming in, and you're, working out the cubic right here and returning the Y. So that's how the spline, that's how you get your data. Once you know your splines, you bring in your X raw data, all of it, and then the point of interest. So that's how I got that Y spline I that corresponded with my 75. And then what I wanted to do is I wanted to see how these splines work, across that whole spectrum. So I went really crazy and created, I guess it's 540 points. Because our raw data is only 11, right? 11 pairs. But I went, all the way from minus 40 up to 500. And I wanted to know, walking through those splines, how's that fine look? And then I'm going to graph. So X fine, Y fine, I'm going to 540 data points. I'm going to see it very nicely. Then I plot it out. So I plot the raw data. I plot as blue. So you're going to see jagged line segments. Then you're going to see the very fine one in green. And then my point of interest, I'm going to see it as a red square. So then I go ahead and label things up. So let's see what it looks like. Right, so here we go. You can kind of see the blues jagged, but the green nice and smooth with the splines. And remember, they're 10 spline segments, but it's going to look like very smooth. I'm going to zoom in a second. So the red square is sort of the 75 point of interest there. So let me zoom in, and zooming in on that 75. You can see it quite nicely. So it's in that segment that goes from 50 to 100, right? So you see the green is the spline segment. So that segment I'm on right now, that green spline segment, is very nicely matching up with the segment that preceded it and the segment that comes next. So that's how it works. So we can see we would have a very nice smooth curve, smooth to the second derivative that goes over the whole data, and we're just in this example focused on 75. How does that kind of fit in? But that would be much smoother than just looking at the raw data, the blue, just connecting the 11 data points. The difference, if I were to just interpolate with just the raw data, we'd shift up a little bit. We'd be there. So the difference wouldn't be really huge here. But if you wanted, a nice smooth propagation of data consistent to, probably 3 sig figs here, then the spline's the way to go. Okay, so we talked about starting off with polynomial interpolation, transitioning into cubic splines. I showed you how to calculate the data for the cubic splines. So I think that is a good stopping point, and you're set up for success. I hope you enjoyed it.